Hi everyone, I'm Jim Clark, Clark Environmental, and welcome to another Clark Environmental's Fun with the Environment. Today's guest, good friend of mine, known for a long time, Mark Alessandroni, Markay Consulting. Mark, give us a little background.
As Jim said, we've been friends for longer than either of us probably care to admit. We've worked together in a variety of capacities over the past probably 20 years, maybe.
Yep.
And Jim asked me to come by today and try to help maybe clear up some confusion and maybe create some more on a couple of topics that are of interest to him and his clients over the years. So I'm happy to be here.
One of the things he's a little shy about is Mark is a PE, Mark is a CHMM, and he's also part owner, he was, of Lab. So what we're trying to do is take the best of both worlds, put them together for today's talk. Let me start off by saying, here at Clark Environmental, we get a lot of questions on what to test, how to test, what to do, this, that, and the other thing. I'm gonna fire some questions at Mark that we get here all the time, and I'm gonna let the expert, we use that term loosely around here, but I'm gonna let the expert go ahead and answer them. Mark, once again, thank you for being here. First question is, I've got all these IDW samples from 20 wells. Environmental engineer comes up and says, and I put everything into 5 drums, all these samples. Afterwards, one well was showing hot. What should he have done ahead of time?
Well, I mean, IDW, we're talking about investigation-derived waste from a groundwater sampling event in this particular example. And so when we collect groundwater samples, we are required by the DEP SOPs to purge a certain volume of water out of that well before we collect the actual sample for laboratory analysis. And so in that process, from shallow wells here in Florida, you may generate 2 to 5 gallons of water for each well. And in the scenario that you presented, a consultant or a technician or someone of that ilk is taking that purge water and combining it into drums at a site that will ultimately need to be disposed of properly. And so I think what your question is we're combining all this purge water from these 20 wells into 5 drums. What can we do to minimize our hassle and expense of disposing of that when somebody like Clark Environmental says, hey, we need to know what's in those drums. And so the easy answer, and what has worked for us over a number of years, is that you would record the volume of water that comes out of each drum, which should be on your groundwater sampling logs. And then when you get the laboratory analytical results back, you can calculate a volume weighted average and know the mass of the contaminants of interest in each drum based on the volume of water that came from each well, and then the concentration reported by the lab for each well. And you want to record which wells went into which drums, and then you can calculate that net concentration in each drum and compare that to whatever your guidance criteria is for interest. If it's IDW purge water, I suspect you'd be looking for, does it exceed the Tclp limits or something like that, as to what we're going to do. One thing to keep in mind is that, and this has never come up in my experience, but it's something to keep in mind, is that if we assume that all the purge water had the concentration that's reported in the laboratory analytical report, then that sort of defeats the purpose for needing to purge the well at all, because we're purging the well to be sure that the sample that we're having analyzed at the lab is representative of what's in the aquifer, and we acknowledge that water that has accumulated in the well since the last time it was purged may not be representative of what's there. So assuming that all the purge water has the same concentration that was reported by the lab for that particular well may not be accurate, but it's never been an issue, and it might be one of those questions you don't really want to know the answer to. So that's what I would say about that. So that's kind of the easy way to do it. If you don't have that information, Jim and his crew are probably going to ask you to take a sample of each one of those drums, have it analyzed by a laboratory, and then use that concentration. But if you want to try to get around to having to do that, and the time and the expense associated with that second sampling effort, just record the volume out of each well, use the concentration reported for each well, and calculate the net mass of contaminant in each one of those drums, and then use that to characterize your waste.
The expert.
Yeah.
Okay?
Don't trust anybody that calls themselves an expert.
Next, if you've got 2 drums, okay, one is a solid, one is a liquid, and you need to run a TCLP. By running a TCLP, what are some of the things that you can help save them money, or things that they should do that is correct?
Sure. So, for the sake of our discussion here, let's assume that we have a drum that needs to be characterized as being hazardous or non-hazardous, and let's assume that for our purposes here, that drum is a soil drum, and that there's no free liquid in the drum. That is, there's no separated liquid phase in the bottom of the drum that we might be able to identify by sight. If there are no free liquids in that drum, then you can either submit that sample to the lab and have them run a TCLP, and we'll talk a little bit here about what that method is and so on and so forth. But you can actually, if it's essentially dry soil, right, no free liquids, you can use the 20-to-1 rule that we hear from time to time to characterize that without having to analyze the sample at all for TCLP. Because there's an inherent 20-to-1 dilution in the leaching process in the TCLP method that would allow us to use that 20-to-1 ratio and back calculate what's the maximum TCLP concentration we might expect. So for instance, the TCLP MCL for arsenic is 5 milligrams per liter. Okay. If we have a soil drum, an essentially dry soil drum, that has arsenic at less than 100 milligrams per kilogram, then there's no conceivable way that the TCLP method would yield a leachate with a concentration of 5 milligrams per liter or higher, because you have a 20-to-1 inherent dilution in the method. That's all fine and dandy. That works out great.
So you're saying say it was 120 milligrams, but what would they have to do then?
So then you would have to run the TCLP, or you could, by all means, you can always assume something's a hazardous waste, right? And so if it's 120, if we divide that by 20, then the maximum theoretical concentration we might expect to see in that drum is 6 milligrams per liter. That exceeds the 5 milligram per liter MCL for arsenic, and that being the case, that would be a hazardous waste. But you can always submit it to the lab and have them run TCLP, and it may be, and it's probably very likely, that not all that arsenic is leachable in the TCLP method. So you could still have a concentration that's less than the TCLP MCL of 5 milligrams per liter, but you wouldn't know that unless you actually ran the sample.
So the best thing is, if you're 120, you can send it out as a haz, which is very expensive, or you can go ahead and say, you know what, let's bite the bullet, run a TCLP. Absolutely. More than likely, it will come out as a non-haz.
It depends on a whole variety of things that we can't predict, but you can assume it's haz, or you can run a TCLP and take your chances that way. And that's what I would recommend in that case. So that's for an essentially dry soil sample. As I said, the TCLP percent solids determination is different than a dry solids determination like we might do in a percent moisture. It's just for purposes of TCLP, the soil can be wet, right? It can be wet to the touch, almost like coffee grounds out of a coffee filter. But as long as there's no free liquid, then you can use your 20-to-1 criteria. There's no requirement to separate those phases. Now, when you have a sludge sample, or a sample that's got a fair amount of liquids in it and a fair amount of solids, the TCLP method requires us to separate those two phases and actually take that solids phase and put it through the leaching process, and then take that filtrate and the leachate and recombine it with the original liquid phase and run an analysis on that combined leachate at the end, and that gives us the TCLP concentration.
What if you got just a little bit of solids, say in the bottom?
You got a little bit of solids. This is the deal with the TCLP. 0.5% solids by mass is what is deemed to be de minimis. If you have less than 0.5% solids in your liquid drum, then the laboratory can assume that that liquid, as it is presented in the sample container, is the TCLP leachate, and they can analyze that. And a totals analysis would give you the same result as a TCLP.
So that would save them money.
It would save them a little bit of money in most cases, yes. If that amount of solids is 0.6% by mass, then the TCLP method requires us to separate that solids phase, take it through the leaching process, and then combine that leachate from that leaching process of the solid phase back with the original liquid, and then analyze that for the TCLP. Now the issue here is you might say, I got a drum of IDW, I took purged water out of a monitor well, and I'm going to assume it's all liquid. Bear in mind that 0.5% solids by weight in a 55-gallon drum is, by my calculation, making some assumptions, about 2.3 pounds of solids in that drum. So you can imagine in a 55-gallon drum, that's not much on the bottom of the drum. Okay. And that would constitute what is significant from a TCLP requirement, but whether or not you need to separate that solids phase or not.
You're talking maybe about an inch.
Yeah, maybe an inch of solids on the bottom is enough to trigger a separation of those. So we go out to the site, the drums have been sitting there for, who knows how long, maybe a few weeks or what have you. Obviously, in most cases, those solids are gonna settle to the bottom of the drum. The technician opens the drum, looks in it, and says, it looks all liquid, because the rusty bottom of a drum looks just like settled, orange sediment in a sample. So maybe he doesn't know there's any solids in there. We're splitting hairs here. Most regulators, in my experience, aren't that concerned about IDW drums to that extent where they want to know those sorts of things, but it's just something to keep in mind.
Another question we get all the time, by the way, thank you. I
Absolutely.
hope that helps everybody out there. Another one we get all the time is about PCBs in soil. When is it haz, when is it non-haz, what's the rule, what do you do, back and forth.
So the question here is with regards to thermal treatment of
Okay.
petroleum contaminated soils, right? And the criteria is how much PCBs or what concentration of PCBs in soil is of concern when we're trying to decide whether we can thermally treat soil. And this is, in Florida, this is governed under Chapter 62.713.510, Parent 7 of the Florida Administrative Code. It talks very specifically about how we handle PCB concentrations and what we do and how we behave or how we conduct ourselves with regards to thermal treatment when we see different concentrations. So the two things to remember here are concentrations of 2 ppm and 50 ppm. Okay, so if you receive a soil sample and you want to know whether I can have it thermally treated or not, you run a PCB analysis. Typically we run EPA method 8082, and we analyze that sample. If the concentrations of PCBs in that sample are greater than 50 ppm, the soil cannot be treated as petroleum contaminated soil in a thermal treatment facility. It's just 50 ppm is too much, and that soil then has to go out for some other treatment, land ban, something hazardous or whatever regulations govern PCBs in waste. Over 50 ppm, no go. If the sample comes back at less than 50 ppm, but greater than 2 ppm, this particular section of 62.713 requires that we either try to find an analysis of the original oil that caused the PCB contamination in the ground,
Okay.
or we get a sample of the oil that caused PCB contamination in the ground, and we have that oil analyzed. If that concentration in the oil is less than 50 ppm, regardless of what the concentration is in the soil, then that soil can be thermally treated. If we don't have access to either the original oil sample or some record of the analytical results of the original oil that caused the contamination in the soil, then we have to very carefully document that we made a reasonable effort to find those results. We were unable to do so, and then that material can be thermally treated as long as the treatment facility, in this case that would be Clark Environmental, maintains those records, those documented records about our efforts to find those original concentrations of the oil. So as long as you keep those records, even if you can't find them, you can thermally treat that soil as long as it's less than 50 ppm. And then of course, if you run the soil sample, your pre-burn analysis, and your PCB concentration comes up to be less than 2 ppm, you can thermally treat the soil with no further concern or effort.
Outstanding. Next thing I want to bring up is, and we get this all the time here, I got a VOA, I got a VOH, I got a VOC. What's the difference?
What's the difference? So VOAs would be considered volatile organic aromatics. VOHs are volatile organic halocarbons, and VOCs would be volatile organic compounds. For our purposes here, we did a quick little illustration, Jim and I, of what the different compounds are. So a volatile organic aromatic has to have an aromatic ring or a benzene ring in it, okay? So in this case right here, this is our VOA. And in this particular one, so you see the aromatic, the benzene ring, this particular compound here is O-xylene, okay? This is orthoxylene. If I remove that, that's toluene. And if I remove that, we got benzene. Those are all VOAs. In Florida, if we ask somebody, a laboratory, to report VOAs, they're going to typically report benzene, toluene, ethylbenzene, O-xylene, and M&P xylene. And then they'll also report methyl tert-butyl ether, which is not an organic aromatic compound, but it's a common contaminant in gasoline, and labs have been reporting it here in Florida with VOAs forever. So that's a little quirky thing that we see here in Florida. But so essentially, in Florida, if you ask for VOAs from a lab, you're going to get benzene, toluene, ethylbenzene, xylenes, and MTBE. There's other volatile organic aromatics, but they're not typically reported by laboratories when you ask for VOAs. All right. So VOHs are volatile organic halocarbons. Now halocarbons can contain any of the halogens in the periodic table, which I don't know if that's on our screen or not, but anyway, it can contain fluorine, chlorine, bromine, iodine, astatine, and something I can't pronounce at the bottom there. I don't even know if that's a halogen anymore. But anyway, so most of the time in our world, VOHs that we think about are chlorinated solvents like tetrachloroethylene, trichloroethylene, dichloroethylene, those sorts of things.
A lot of those from like the dry cleaning
From
program.
dry cleaning programs and that sort of stuff, absolutely. So for our examples here, this is a common VOH. This right here happens to be trans 1,2-dichloroethylene. And this is a VOH that is often a degradation byproduct of dry cleaning solvent contamination. And so if somebody asks you for VOHs, this would be one of the compounds you'd expect to see, along, as I said, with tetrachloroethylene, trichloroethylene, vinyl chloride, bromoform, chloroform, all that stuff. Those are all halocarbons, volatile organic halocarbons. And then we have VOCs, which is volatile organic compounds, which is sort of an all-encompassing, it includes VOAs, VOHs, and other stuff that's not typically included amongst the VOAs or VOHs. And our example here that we have drawn on the board, this is acetone. And so acetone is a volatile organic compound. It's not classified as a volatile organic aromatic, and it's not classified as a volatile organic halocarbon. So that's sort of the skinny on all the different types of volatile organic compounds.
Another thing we get asked all the time, and from landfills, from environmental engineers, people doing cleanups, et cetera, is what's the difference between a Tclp and an Splp?
All right, so Tclp is a waste characterization method. If you're not trying to characterize a waste, you don't need Tclp. Splp is a site assessment or site characterization method, typically when you're doing a contamination assessment of a property. So if you're dealing with waste, you want to deal with Tclp. If you're dealing with a site assessment, you typically will deal with Splp. The methods are similar in some ways and different in others. Both methods attempt to mimic the leaching of contaminants from some parent sample to a leachate of some kind using dilute acid solutions. In the Tclp method, we use a dilute acetic acid, dilute vinegar type solution, the pH of which is determined by the initial alkalinity of the sample that you're going to analyze. And the method is intended to mimic the leaching of these contaminants from buried wastes in a landfill over the course of 30 years or so. The method requires that we take the original sample, do some initial determinations, and then extract that sample in a rotary extraction apparatus at 30 plus or minus 2 RPMs. I'm sorry, no, yeah, that's right. 30 plus or minus 2 RPMs for 18 plus or minus 2 hours in a room that's maintained at 23 plus or minus 2 degrees C.
Somebody made big money out of that.
So the labs have this is not an easy thing to do. So people say Tclp lead, you're charging me $35. Why are you charging me $35? That's a good deal when you think about all the things that have to go into this. So anyway, so that's the Tclp method, and we do this on waste. And then you take that leachate that's generated, you analyze that, and you compare those results in milligrams per liter for all those target analytes to the Tclp MCLs that we find at 40 CFR, I think it's 261. Okay, so there's a list of compounds that we look for. So that's Tclp. Splp, we're doing the same extraction, the same temperatures, the same RPMs, but we're using different acids and a different leaching solution. Now, in the Tclp, we said we use a dilute acetic acid solution. In the Splp, we're using a dilute nitric and sulfuric acid mixture that's intended to mimic slightly acidic rain, and whether or not that acidic rain percolating through a soil is likely to leach contaminants in that soil out of the soil phase and into the groundwater and cause groundwater contamination. And the determination, and there's a couple different solutions that we use based on an initial assessment of that soil sample. And believe it or not, in the Splp, we make a determination of which leaching solution to use based on whether the sample originated from east of the Mississippi River or west of the Mississippi River.
Really?
As crazy as it is.
What are the acids? What do they use for?
So they're using, so again, for Tclp, we're using acetic acid.
Okay.
A dilute acetic acid solution, pH 5 and change. And in the Splp, we're using a dilute solution of nitric and sulfuric acid, and the reason we're using those is they're associated with acid rain.
Okay.
And so the idea of coming from east of the Mississippi River or west of the Mississippi River has to do with the prevalence of slightly acidic rain in those regions. And of course, we all think of acid rain in the industrial northeast of the United States and that sort of stuff, and its migration across the eastern half of the country. That's why we do Splp with those acids and used in that solution, and why we make a dividing line of the Mississippi River, because it just happens to be convenient.
That's crazy.
That is crazy. It is crazy. But again, Tclp, waste characterization,
Okay.
Splp, site assessment, or site characterization.
Got it. I got people coming up to me all the time and say, listen, I've got a VOA, or I've got something else, and I want to put it in a jar, and I got it half full, and I'm going to let it sit there, and I'm going to do that. And I keep telling them, no, you got to be careful, because there are holding times that you're going to be careful of. And there's also head space and all that. Explain holding time, head space, and all that for somebody.
Sure. I mean, the idea in the whole sampling and analysis process is that the sample we submit to the lab should be representative of the sample that was collected in the field. In other words, we don't want the sample characteristics to change from the time we collect the sample until the time the lab analyzes it, because then it's no good. It doesn't tell us anything. And so what we want to do is we want to be sure that the sample that gets to the lab is representative of what we sampled when we were in the field. Headspace, temperature, all these different things. There's a table in the FDEP field sampling SOPs. It's under FS 1000, and it's table FS 1000-6, which talks about all the different preservation requirements for different purposes. You have soil assessment in soil samples for volatiles, or for pesticides, or for PCBs, or for semi-volatile, any of that stuff. Where you might have water samples and what the requirements are. Do you need acid? Don't you need acid as a preservative? Zero headspace, these sorts of things. And so the idea is that, particularly with regards to headspace, for volatiles are volatile, right? They have a propensity to leave the liquid solution they're in and partition to the gas phase, the air phase. And so if we have headspace in a sample of water that we're trying to have analyzed for volatiles, those volatiles that are in the water can leave that water and partition to the air phase, and then they're not there when we analyze it. So that what the lab is analyzing in the water isn't what was originally there, because they've left. So we want to have zero headspace. We also want to keep the temperature low on water samples. We don't want to make it zero, because if we have a zero headspace container and we freeze that sample, what does water do? It's going to expand and it's going to break the vial, and then it's no good. You can't do it. So with soil and volatiles, we have a little different procedure. We have, again, this is here in Florida, but we'll have typically two 40 milliliter VOA vials with a little stir bar and some water in them, and then we'll have one that has just methanol in it, 5 milliliters of each. And the idea is that we have a low-level analysis for volatiles in soil and a high-level analysis. And so the low level will come from the water vials in the laboratory, and the high level will come from the methanol vial. They have headspace, but the idea is that the water vials eventually will get frozen. They're supposed to be frozen within 48 hours of the time they're collected in the field. There is some disagreement between the different DEP offices as to whether we consultants are qualified to freeze these samples or not, but that's an issue for another day. But if you can't get them to the lab within 24 hours, freeze those samples. And that preserves those volatiles in that liquid phase, and they can't partition to the gas phase, and that's why we do it that way. In my experience, when we're seeing pre-burn analysis or waste samples characterization, these samples aren't typically collected under the most ideal conditions, right? You're doing an emergency response on the side of the highway, and the guys are trying to grab a couple pre-burn samples, and they got trucks running by them, and it's the middle of the night, and it might be cold, and it might be hot, there might be a whole variety of reasons they don't have access. They're just trying to make this problem go away on the side of the highway. So a lot of times when I ran the lab, we would see people come in with a Ziploc bag full of soil and say, I need a pre-burn analysis. Or they might have an 8-ounce jar, they might bring it to us, and that sort of thing. Technically speaking, does that preservation meet the requirements? No, it does not, but there is a caveat in a footnote to this table that we talked about that actually mentions specifically that no preservation is required for concentrated waste samples. And nowhere that I'm aware of do we define what constitutes a concentrated waste sample. I think we have reasonable inferences about what those might be. But nonetheless, you could argue that this is a concentrated waste sample and may not need preservation. But to remove any doubt, and if you live in a world of litigation like I do from time to time, somebody might rebut the validity of your results if you submitted a pre-burn sample in a Ziploc bag and then you didn't have all the right preservation. And the lawyers get involved, and it may be a problem. So if you want to be careful, follow that table specifically. If you're feeling lucky, you might fall back on that caveat that no preservation is required for concentrated waste samples.
Last but not least, this is a biggie, which is tough, and pay attention, everybody, because we get stuck with it all the time. Rules and charts for PAHs.
Yeah, in Florida, we deal with something called benzoate pyrene equivalents when we're trying to assess soil contamination associated with polynuclear aromatic hydrocarbons, right? So, depending on what method you request and what lab you go to, you may have 16 or 18 of these PAHs reported, right? So, of this group of PAHs, there's a subset of 7 of them that are deemed to be carcinogenic, and these are the ones that are of primary concern to us when we're dealing with these benzoate pyrene equivalents. Of course, one of those PAHs is benzoate pyrene. The other 6 are benzo A anthracene, benzo B fluoranthene, benzo K fluoranthene, chrysene, dibenz AH anthracene, and endino 1,2,3-CB pyrene. Now, rather than having soil cleanup target levels for each one of these compounds, somebody a lot smarter than me, developed a criteria where we have toxicity equivalence factors. And so we know that benzoate pyrene is the most carcinogenic of these 7. And then through a series of risk assessments and research and analysis and a whole variety of other things that I'm not smart enough to understand, somebody determined that we have toxicity equivalents that are fractions of the toxicity of benzoate pyrene. And we're fortunate in Florida because the state of Florida gives us this cool little table and calculation spreadsheet that does all the hard work for us. But essentially what we see if we look at this is that benzoate pyrene has a toxic equivalency factor of 1. And then some of the others, like for instance benzo K fluoranthene, is deemed to be 1/100th or 1% of the toxicity of benzoate pyrene. So it's not as toxic. Benzoate pyrene is 100 times more toxic than benzo K fluoranthene. So for the other 5 or 6 carcinogenic PAHs, we have toxic equivalency factors. We put the concentrations that are reported by the lab into this spreadsheet, again, that's provided by the DEP for us, and it tells us whether or not the net toxicity of that sample with regards to these carcinogenic PAHs meets or exceeds the soil cleanup target level for the residential direct exposure.
So all you gotta do is get the analytical that you provide,
That the lab provides, right?
and then go ahead and plug it in,
Yep.
and everything's calculated automatically.
Everything's calculated. What I would tell you is using this table, don't get crazy with trying to change significant figures or anything like that, because this table actually works to our benefit. Even so if you look at the rule, the soil cleanup target level for benzoate pyrene is 0.1 milligrams per kilogram. It's not 0.100, it's 0.1. Most people don't care about significant figures, but we chemistry kind of people, we do from time to time. And to our benefit, this spreadsheet that's provided by DEP actually allows us to have as much as 0.149 milligrams per kilogram. But due to the rounding rules employed in the spreadsheet, it will tell us that it actually meets the soil cleanup target level and no further action is necessary.
So you can have above point
You can
one.
have 0.1, you can have 0.12, 13, 14, up to 0.149, and it still will meet the criteria of 0.1 based on rounding rules that are employed in the spreadsheet. So just because you get the analysis back and you calculate this benzoate pyrene equivalence as 0.122 per DEP in their spreadsheet that they provided to us, that's not enough to exceed the soil cleanup target level.
Get out.
It's crazy. It's one, I dare say, rare example where we, the regulated community, have something that actually benefits us. So that's not bad.
Well, those are the common questions we get here at Clark Environmental. I know we threw a lot at you today, so I just want to say that if you have any doubts, if you have any questions, you want to know anything, we're going to keep this video up from now till April or longer. Just review it, go over it. If you don't understand anything, send us a note, a question, whatever you have, to CEI@clarkend.com. And next month, what we'll do is we'll answer it. We'll try to help you out, any questions you have. And if we pull your name out of the hat, it's a $100 gift card for you from Clark Environmental. I guess you've seen why I asked Mark here today. This stuff is like, oh, right over here, okay? Mark, I know we gotta be careful with COVID. I can't thank you enough for coming in, helping out, and trust me, Markay Consulting is who we use here. So he's just not a good face and a good name, he's also a very, very good engineer. P-E-C-H-M-M, thank you.
You're very welcome. Thanks for that.
And until next month, see you then.